questions that we need to address before we get going? Okay, of course not. Why would you guys have questions? Okay, cool. Let me set this up. And share my screen. Yeah.
Oh yeah, never mind. Someone's not, one of my groupmates not coming to lab.
Oh, well, that's too bad. It's a good lab.
I know, but his mother and brother got COVID.
Oh my God.
He'll join us for Discord.
That's okay. That's okay. Your group has had bad luck.
What do you, okay, by what? The absent or that our material usually have a dead battery?
No, yeah, the absences. You guys are full of germs. I got to tell you. Okay.
Two people.
Or your hand.
I'm fine. I know.
Wait, yeah. Okay, where were we last time? We were talking about capacitors, right? And we had like our AC source and we had it hooked up to a capacitor like that. We went through our Kirchhoff loop and we said the voltage of the source minus the voltage of the capacitor needed to add up to 0. We played, tell me if I'm missing, like tell me if I'm not where I'm supposed to be. Because I completely kind of forget where we were. We said the voltage of the capacitor was Q over C, and then that gave us that since the voltage, the source voltage was Vmax sine omega t, then the Q had to be C times Vmax sine omega t. We, of course, took the derivative of that to find the current. Which was a cosine. And so we had Vmax omega c cosine, like that. And then we started defining things like the reactance of a capacitor, 1 over omega c, where omega is that angular frequency, 2 pi f. Andrew drew a phase diagram where we had talked about these waves, this current and this voltage being these sine waves that might not always be in phase, because here we have our source voltage being a sine function and our current being a cosine. So they're not going to hit their peaks at the same time or hit their low spots at the same time. So they're not in phase. Where you could draw a picture like this to demonstrate whether something is in or out of phase. But that's hard to do. And so instead we just draw this phase diagram where we say, okay, like the voltage across this capacitor is 90 degrees behind the current going through that circuit. And that is indeed the phase difference between a sine wave and a cosine wave. Sound reasonable? Okay. And yeah, just tell me if I'm in the wrong spot. I forget where I left off, because that brings us to inductors. Let's see, I feel I did. There you go, inductors. Sorry, notes are not perfect. Okay, inductors. Okay, let's look at the inductors next. So the idea is we're kind of building up to an all-over circuit. So now we've done resistors, and we know how resistors behave. Now we've done capacitors, we know how capacitors behave. Then we'll do inductors. And then at the end of the day, we can add them all together. So we've got the capacitors, we've got the resistors, let's do some inductors. Inductors. Okay, so an inductor I have, same thing, we do the simple problem first, and then we add our simple problems together to get a big complicated problem. So the simple problem with an inductor is just a source and an inductor. And we loop this around. So our source voltage minus the voltage across the inductor needs to add up to 0. We remember that the inductor voltage is L di dt, and that's what we got from the last chapter, right? Where the inductor just tries to oppose changes in current. Okay. Then we kind of put this all together. So my source voltage is still Vmax sine omega t. My inductor voltage, di dt, needs to add up to 0. I'm looking for an equation for current, so I want current on one side of this equation and everything else on the other. So I'll move this whole thing to the other side. So I'll have dL di dt equals Vmax sine omega t. And then I'm going to multiply both sides by dt, which will make sense, I promise. And I think I'm dividing both sides by L, right? Yes, and I'm dividing both sides by L. So on one side I have di, and on the other side I have Vmax sine omega t over L times dt. Okay, I feel this is about where we left off last time. This seems kind of familiar. Okay, and knowing that I want an equation for current, now I'm just going to integrate both sides of this equation. As long as I do the same things to the same sides of the equation, I'm good. So integral of di, just I. Vmax and L are both constants. So I'm really integrating sine omega t. I did do this last time. Where we're going to do our u substitution, because I can't put my constants in the right place, where u will equal omega t. So du equals omega dt, or even better, dt equals du over omega. Okay. Plugging in everything, du over omega. And omega is just a constant, so we're going to pull that outside. What is the integral of sine? Negative cosine, excellent. So I have Vmax, I'm gonna put that omega out with my constants. I have a negative cosine of u. I will, of course, first thing, get rid of that u, because it was only just a placeholder. Sine omega t. Sine omega t, that's silly. Negative cosine omega t. Okay, that looks better. This looks much better. Okay, and this is the current through this circuit. Okay, so let's talk about how this is going to look. Let's draw this first off. Okay, so my source voltage, put it in blue, is Vmax sine. So my source voltage looks like a sine. Okay, there's my source voltage. Then my current, put it in green, looks like a negative cosine. Okay, so that means it's gonna, instead of starting at the top, it's gonna start at the bottom. Here, I'll draw it like this. There, it's its maximum. So when the voltage is at 0, it's hitting its mins or max. When the voltage is at its mins or max, it's hitting its zeros. Okay, so that's my current. And this is time, and this is like either voltage or current. Kind of a weird graph because I'm putting my currents and my voltages on the same axis, but I'm just trying to compare their patterns, not really their magnitudes. Okay, now when I look at this, this is the voltage with the inductor. Does my current lead my inductor or does it lag my inductor? But is my current ahead of my voltage or is it behind my voltage? And it's gonna lead because, so like if you think of this as 1 second and this as 2 seconds, so my current, am I doing this right? I think I am. Yeah. So my voltage hits its peak, and then a second later, my current hits its peak. So my voltage is leading my current. Sound okay? And in fact, it is leading my current by 90 degrees. There's a couple ways to see this. One is just kind of like visually knowing what we know about sine and cosines. If one is at its peak when the other one's at 0, that means that we're 90 degrees out of phase. Make sense? You could also pop over to your trig identities, and you could say, I know that a negative cosine is a positive sine of that angle minus pi by 2. So that negative cosine is pi by 2 ahead of my sine. Okay, which leads us to our phase diagram. Okay, where we're going to do this the same way. We're going to put our current along this axis, and we're going to put the voltage on the inductor. It's 90 degrees ahead, so it's going to go like that. Does that make sense? Okay, okay. Hold on to that for 10 minutes while we dissect the rest of this equation. Let me write this again. I of t negative V max over omega L cosine omega t. Okay. Well, if this is a current, then certainly this thing out front is the amplitude of my current, right? So that means whatever the current through this circuit is, the maximum current is equal to V max over omega L. And we're going to do the same thing with this that we did with the capacitor, where we want to make up an equation that looks like Ohm's law. We want to have a V equals I times some like resistance like quantity. And for that to be true, we're going to take this equation, we're going to say, okay, V max equals I max times omega L. And we say, well, omega L, that has to be our resistance-like quantity. Sound okay? I hope so. So we define a quantity called the reactance of an inductor. It equals omega L. And remember, omega is 2 pi f. So this is really 2 pi f times the inductance. Just like our other reactance, it is measured in ohms. Kind of good kind of stuff in there. It's measured in ohms. And of course, we call it a reactance instead of calling it a resistance, because it's not resisting current, it's just reacting to that current. This is an inductor circuit, so that it's not that the wire has whatever ohms amount of resistance, it's that when the current changes, it tries to block it. And so this just tells us the value of how good it is at blocking current. And I kind of like to point out that it is dependent on the frequency of the source. So that F, that's a frequency of the source, whatever's coming out of the wall, right? So let me ask you, this inductor. So I'm running AC current through an inductor at a high frequency. Will my reactance go up or down at high frequencies? So if I have a big frequency, do I have a big reactance or a small reactance? Just follow this equation. It should be big, because as F goes up, chi sub L will go up. Does that make sense? Okay. If it's got a big reactance, does it want to let a lot of current pass, or does it not want to let a lot of current pass? So if I have some voltage here, current will decrease. So if my reactance goes up, current has to go down. And we can, of course, say the opposite for low frequencies. If my frequency goes down, my reactance goes down. And so my current would increase in that case. Okay. And so what this means, and I kind of hope this, I kind of hope this makes sense, because if you think about an inductor doesn't like change. Like, that's the whole thing about it. You know, the Faraday's law, it wants to remain the same. And so of course it doesn't like high frequencies because high frequencies change very quickly. That's the whole point of frequency. It tells you how much something changes. And so if I put two currents across the same wire, one with a very high frequency and one with a very low frequency, the low frequency would get through, but the high frequency would not get through. It would get blocked. And that is what you would call a low pass filter, because it would pass all the low frequencies and it would block all the high frequencies. Does that make sense? Okay, okay. So I have that. This all looks pretty good. Do I have enough? So we have resistors, we have capacitors, we have inductors. Let's put them together. All right, here it is, the payoff. Okay, so I have our LC circuit. I have my AC source. I have a resistor. I have an inductor. And I have a capacitor. RLC. They're all in series. So one thing we're going to say that they all have in common is the current. The current has to be doing the same thing at the same time for all of these pieces. However, if we look at the voltages, voltage of the source has to equal the voltage minus the voltage of the resistor, minus the voltage of the inductor, minus the voltage of the capacitor. Well, all the voltages need to add up to 0. They could all be doing different things at different times. So at some point in time, you might have a big voltage across your capacitor and a small voltage across your inductor, or vice versa. It just, at any point in time, they need to add up to 0. Okay, okay. And so here's the thing. So now what we want to do is we want to draw a phase diagram to talk about how each of their voltages are going to relate together. And so let me write out the equation, and then we'll talk about the principle of adding things together. What's the principle of adding? Superposition. The principle of superposition. Okay, so the source voltage equals all of these things. And then we can look at all of these things put together like this. So my source voltage equals this. And now remember, this is how we figured every little thing out. So this is how we got this current with just the capacitor. We had that equation. And this is how we got the current with just the inductor. We had that equation. And in fact, if you look back, that's how we got the current with just the resistor. We had that part of the equation. And so all we've done is we've added our solutions together, which means we're just going to add everything up. Okay? And so let's look at what it means to add these solutions together. It means that I'm going to have a phase diagram where I'm going to put my current along the axis like that. Okay, I'm going to put my current along the axis like that. And then I'm going to draw the voltage across my resistor. Do you guys remember on Tuesday when we did resistors? Was the voltage across the resistor in or out of phase with the current? It was in, right? Because the resistor just burned current. There was no like time dependence where it was saving up charge or trying to block current. It was just more current goes through, I burn more current. So I will draw that in phase by just drawing it in the same direction as my current, where I'm going to remember The voltage of my current equals just I times R. The lengths of these lines don't really make a lot of difference between the current and the resistor, current and the voltage, because those are different quantities. I'm just the directions matter more than that. Okay, now I'm going to draw the voltage across the capacitor. Now, again, the voltage across the capacitor is going to lag by 90 degrees. It doesn't matter so much that there's other things involved here, because the whole function of the capacitor is that it lags behind the current. Whatever the current's doing, the capacitor will do 90 degrees later. Okay, shoot, I needed that back. And then last of all, I have my inductor, and my inductor leads because this inductor, whatever it's doing it 90 degrees before the current doesn't. Is that okay? So now if I wanted to add these voltages up, so I want to add these voltages up like this, because I want to find the source voltage, I need to add them up like I would any vectors that are two-dimensional. I need to make a triangle. Does that make sense? So now I'm kind of looking for what the source voltage is. And the source voltage is all three vectors added together. But since I put this time dependence on it, I need to treat it like that. So I'm adding my VL to my VR to my VCAP. Since my VL and my VCAP are in the same dimension, I just add them together with the inductor being positive and the capacitor being negative. So the overall vertical voltage is going to be smaller than it was before because I'm subtracting off that capacitor. Okay. And that means that my source voltage looks like that. Notice I made that triangle. We'll draw it bigger over here with the voltage across the resistor on the horizontal component, and the vertical component is the voltage across the inductor minus the voltage across the capacitor. Sound okay? And if it sounds okay, you might think to yourself, what are you going to do with this? And you would be quite right. What you're going to do with this is you're going to find the total impedance of a circuit, and you're going to find the phase of a circuit. So the total impedance of the circuit, we kind of have these little reactances, right? So like we have this reactance here, where basically I wanted to know how this inductor was going to block current, and so I made something that looked like an Ohm's law. And I just said, okay, whatever is in where you would have put the resistor, I'm going to call that a reactance. And I did the same for capacitors. We said, whatever we made an equation, V cap equals I reactance, and whatever we found in that reactance place, that's what we put. That's what we said the reactance of the capacitor would be. And now I'm adding a term. I'm going to say Z. We're going to call that impedance. And we're once again inventing a new name because we want to include reactances and resistances. And since they're all different mechanisms, we're just going to call it this overall word impedance, where impedance impedes current. However it manages to do that. Sound okay? And we can write down this Ohm's law equation that says if we look at the total voltage through the circuit that equals the current times the total impedance of the circuit. So when you're seeing that Z, that really means that you're taking the total impedance of the circuit, the resistors, the capacitors, the inductors, whatever's in it, just all of it together. Sound okay? I hope it does. Okay, looking at this, I know that the voltage across the resistor equals I, the current times the resistance. I know that the voltage across the inductor equals I times that. And I know the same thing for the capacitor. The voltage across the capacitor, I times its reactance. And so if I want to talk about how to add all these reactances and resistances together, a good way to get there would be through the voltages of each component. So that's what I'll do. I'll say, why can't, over here, I replace that source voltage with a bunch of these other voltages, see if maybe we can get current to go away, and then express Z in terms of R's and chi sub L's and chi sub C's. If you wanted to write an equation that included the hypotenuse of this triangle and the two legs of this triangle, what equation would you write down? Of this right triangle, you would write down the Pythagorean theorem, where you'd say the hypotenuse equals each leg, hypotenuse squared equals each leg squared added together. And then you'd say, well, for the source voltage, I know I have some current times the total impedance of the circuit. And my resistance, current times the total resistance of that circuit. Same thing with these guys. I have the current, that's not squared, times the reactance of my inductor, and the current times the reactance of my capacitor. Okie dokie. I can pull that I outside of the parentheses. It will become squared when I do that. So we'll have an I squared, Z squared, I squared, R squared, plus I squared, this thing squared. Can I cancel out those I's? Excellent. Let me ask you a trick question. Were those I's maximum values or RMS values? It was a trick question. Because I'm really hoping everyone's going to tell me it doesn't really matter. It doesn't really matter. I think I wrote it down with everything being a max value, but you can write it down with it being an RMS value, right? Because the way to get back and forth between RMS and maximum values is just divide or multiply by root 2. And so you can have Vmax equals Imax times something, or you can have VRMS equals IRMS times something. But to get back and forth, you're multiplying them by the same root 2, so it doesn't really matter. Sound okay? Okay, cool. Which is why I stopped writing subscripts, because I don't like writing subscripts. But this ends us up with a very nice equation where the total impedance of my circuit equals the square root of R squared plus X sub L minus X sub C squared, all square rooted. Do remember that this is 2 pi F times L, and chi, these are chi's, they're not really X's. And the capacitor reactance is 1 over 2 pi F times C. All right. First off, everyone good there? Let me come back. There's stuff I want to talk about there, but let me come back around to it. And let's talk about a phase angle first, where a big question here that we're asking is what's in phase, what's out of phase. And so when you characterize an AC circuit and you say it's in or out of phase, you are referring to the source voltage and the current. So that's what you're saying is in or out of phase. Where you, to say how in or out of phase it is, you refer to the phase angle, which is the angle between those two things. Which, again, if you look at this triangle, you can certainly figure out what that phase angle is with those two sides, your opposite and your adjacent side. If I'm using the opposite and adjacent side of this triangle, what trig function do I want? I want a tangent. So the tangent of the phase angle is the opposite side over the adjacent side. And we can simplify this down even more by saying I have a current times chi L minus a current times chi sub C over, this is a voltage, that's not R, that's a voltage, over a current times my resistor. Sorry, I don't know why I didn't have that as a voltage. I have as the voltage. There we go. I can cancel out all these I's. Boop, boop, boop. So my phase angle is just the reactant, the difference of the reactances divided by the resistance. Okay, is that all right with everyone? I would like to talk about power and why we care about that phase angle. So, power. So first off, let me get resistors out of the way, because power is going to be weird with the capacitor and the inductor, because they're not burning energy, they're just saving it for later. So they're doing weird things with the energy in this circuit. The resistor is doing something really straightforward. You put a current through it, it burns the energy. So for the resistor, you just are looking, you can, you're just looking at an I squared times the resistance. One way to write this down is you can write it down as like an I max sine squared omega t. Remember that your resistance, your current through your resistor is in phase with the voltage, so you get a sine. And so this gives you a really, I max squared, a really instantaneous value for power. So if you wanted to know how much power your resistor, energy your resistor is burning off per second, like at any point in time, that's what you do. But I'm kind of hoping that you guys realize that that's not super useful, because your current is running at 60 hertz. And so you wouldn't want to track every 60th of a second. So you might want more of an average power. So we'll take the average of this thing. And so I need to take the average of that. And then I need to take the average of this. So first off, let's start with the easy part. I max squared, is that a constant or is it going to change? It's a constant. Okay, so I don't need to do anything to take the average. It's just I max squared. Okay, sine squared. Think back to Tuesday. What's the average of sine squared? What's the maximum value of sine squared? What's the maximum value of sine? No. So like just one. Okay, and what's 1 squared?
1.
1. Okay, so the maximum value of sine squared is 1. What's the minimum value of sine squared? It can't be negative because it's squared. 0. Okay, so sine squared runs from 0 to 1 symmetrically. And so the average of sine squared is right in the middle at 1/2. Vaguely familiar? You guys did not watch the recording from Tuesday. Okay, so there's my 1/2, which means I'm gonna write this fancily. I'm gonna write this as I max squared over root 2 squared. And I'm hoping you see that we have an RMS value at this point, because I RMS is I max over root 2. That's what you missed from Tuesday. So I have an IMAX, I have 2 IMAXs on top, I have 2 root 2s on the bottom, so I really have an IRMS squared. And that is the average power and a resistor. Sorry, I lost my resistor. This guy, that guy, that guy. There's an R on that, because power is not the same as current. IRMS squared times my resistor. That's my average power. Man, I'm having trouble writing this. Okay, cool. Average power through my resistor. So that's how you deal with your resistor. It's just burning power at an average IRMS squared times the resistance. Okay, now let's look at the more complicated components. So now if I want to think about how this circuit is going to burn power, I need to think about the current through the circuit versus the voltage of the source. So for that one, I'm going to look at power equals current times voltage, because they're both doing things. Okay, let's run my voltage at V max sine omega t, because that's a good place to start. And then let's look at my current. Okay, looking at this, my current is whatever my source voltage is minus the phase angle. So wherever my source voltage is, if you subtract off the phase angle, you get the current. Does that make sense? So I'm going to write down my current as I max sine omega t minus the phase angle. I'm going to write V max. Okay. Sound all right? Hope so. Okay, looking at this, let's start clumping things together and see what we can do here. Let me put my I max and my V max together, because those are constants. They're time independent. And then I have this sine omega t and sine omega t minus phi. We're going to think way back in our heads, and we're going to pull out some trig identities. And the trig identity that we are going to pull out is that the sine of A minus B equals the sine of A cosine of B minus cosine of B, oh, cosine of A, sorry, cosine of A sine of B. Okay? And then this thing's going to become, I got I max, I got V max, I got sine of omega t cosine of phi minus cosine of omega t sine of phi. And I'm multiplying that by this extra sine omega t out there. Okay, look good? I hope it does. Let's multiply through my sine omega t. I promise you this is leading somewhere. So I have a sine squared omega t cosine of phi minus, let me just say sine, I'm going to have a sine, a cosine, and then another sine. A sine, a cosine, and then that sine phi. Okay. At this point, we're going to take our average. Okay, so just like a resistor, we really don't care about an instantaneous value. We care about an average value. So let's take an average of this, and let's talk about what's going to happen. So these Imax and Vmax, is that going to matter if I take an average? Will that change at all? No, those are just constants. So those are going to pull through. What about these guys? And in fact, let's just make this easy. What's the average of a sine function? Someone's going to tell me 0, right? 0, right? Because the sine ranges from +1 to -1. And then this is why you need an RMS value if you're going to take an average of a sine function. But you just take an average of a sine, you hit the middle and you get 0. So when I take an average of this thing over here, you're going to get 0. You just have the thing in the beginning. And that's nice, because we know that the average of a sine squared is 1/2. So this guy is going to 1/2. Looking at this cosine of phi, is that a constant or a variable? And you're gonna answer that by telling me the angle, the phase angle, is that a constant or a variable?
Variable. Yeah, constant.
Constant, right? Because with this picture, all these things are rotating, right? They're all rotating at whatever angular speed we have, but the relations between them are going to stay the same. VL is always going to be 90 degrees ahead of the current, and so they'll just circle like that. Which is why we don't draw it as a circle, because you really don't need to know that what it is at any one point in time. We just need to know the relationships between them. Okay, but if cosine of phi is a constant, it's just going to hang around like Imax or Vmax would. So that means the average power in my AC circuit, I got an Imax and a Vmax, and then I have a cosine of phi times 1/2 minus nothing. I don't even really need that right there. Okay, and let me write this, just because people usually write it like this. This is 1/2 Imax Vmax. And people write it like this because they care about this cosine of phi. It's called the power factor. Where if the phase angle is 90 degrees, what's the cosine of 90 degrees? Cosine of 90 is 0. Yeah, 0. So that means that the average power in your circuit, if your source voltage and your current are 90 degrees out of phase, is 0. 0 power. Okay? What if your phase angle is 0? What if you are completely in phase? Yeah, that cosine of phi will give you 1, and that'll give you the maximum possible power you can get out of your circuit. And so that's why this phase angle is so important, is it tells you how much power you can get from this circuit. Because you can be running a really high current at a really high voltage, but if they're not in phase, you're not going to get anything. Because if you remember, so for those of you who are in lab, several weeks ago, we had a bunch of 6-volt batteries when we were doing that short circuit lab. A bunch of 6-volt batteries that could barely put out current. Sound vaguely familiar?
Yes.
Okay. And we have some 6-volt batteries that can put out a lot of current. And so when you're looking at power, you don't just care about the voltage. You need to be able to provide that current at a voltage. That's what's giving you all this energy. And so if every time your current's at its maximum, your voltage is at 0, you're never going to get anywhere. And so that's why something like this, where you notice your voltage is at its maximum, your current's at 0, or your current's at its maximum, your voltage is at 0. The power coming out of here, you're not getting anywhere because your current and your voltage are 90 degrees out of phase. Okay, happy-ish? All right. Really quick, just so you guys can see it. If you want to talk about your power factor in terms of your inductors and your capacitors and your resistors, you would go back to this triangle here, because you still really care that that's still your phase angle. So the cosine of that phase angle would be the adjacent over the hypotenuse. So the cosine will be the adjacent over the hypotenuse, which of course we can write down in terms of a current times the resistance and a current times that total impedance that we were talking about. And our current will cancel out. So our power factor is R over Z, where Z was that big Pythagorean theorem thing. Okay. Sound good? Excellent. Then, okay, yeah, no then. Then I want to talk about resonance, because I'm hoping that you guys see that what you really want is you might want a very powerful circuit. And so you would want to maximize this power as much as possible. And if you want to maximize this power as much as possible, what do you want this phase angle to be? Yeah, I want my phase angle to be 0 because I want the cosine of that angle to be 1. Okay, so I get maximum power when my phase angle is 0. Okay, looking at that, that would mean that I need this component to be 0 for that to work. So whatever my inductor is doing, voltage up needs to cancel out with voltage down. And that way, my source voltage and my current through the circuit will be completely in phase. Okay, so if I want to hit resonance, what resonance means is that you are at a maximum power, and we're going to talk about resonance some more. You need the voltage of the inductor to equal the voltage of the capacitor. And this is pretty straightforward. If you want the voltage of the capacitor and the voltage of the inductor to be the same, you just say, okay, I need the current times the reactance to equal the current times the reactance. And you cancel out your currents, and you say the reactance of your inductor is omega L. The reactance of your capacitor is 1 over omega C. So your resonance will occur when the angular frequency of your circuit equals 1 over the square root of LC. Okay, so let's talk about this in a few ways. One, I hope this is somewhat familiar because we did LC circuits DC a couple weeks ago, and we found resonance at the same spot. And basically the same ideas of resonance apply. So I don't remember how much I talked about it back then. But if you think about something oscillating and you want to put energy into the system, you push it, right? You give it a push. But it's really important that you push it in phase with the way it is naturally swinging. So like if it's coming down this way and you push it on the way down, you're not putting energy into the system, you're taking energy out of the system. You have to push the same direction it wants to go. Sound okay? So you need to be in phase with your circuit. Now, inductors and capacitors, they're those harmonic oscillators that have their own phase. Like capacitors will collect charge at a pace that is inherent to their capacitance. Inductors make magnetic fields at a pace that is proportional to their inductance. And so they will want to bounce their energy back and forth at a certain frequency. And so if whatever is coming out of your wall matches up with this frequency that the inductor and the capacitor want to bounce back and forth at, then you'll hit this resonance where you can collect a whole lot of energy in your oscillator. In fact, that's kind of a system that's pretty easy to blow up. I don't know if you've ever seen like those pictures of like soldiers walking across a bridge, and if you hit it like at the resonance of the bridge, you can break your bridge. Kind of the same thing with the wine glass. If you can like hit a certain note, you resonate it and it shatters. So if you hit this resonant frequency, you're not dissipating any energy, you're just gathering it together. So you do kind of have to be aware of that. But you know, throw a resistor and you'll be fine. Okay. Does that make sense? Everyone happy with that? Okay, I am running towards the end, and I think I have just enough time to talk about transformers, which is really good because that's the last thing in this chapter, and transformers are really important. And it's kind of a weird thing to talk about because it's a kind of, it's not it matters for AC, but we're gonna kind of jump to a completely different topic for a second, and I'll tell you why it's important at the end of it. So transformers. I mean those big power transformers that you see like at the end of a city block. Okay, What those do kind of two things. One, they isolate your power generation from your power consumption, which is good because if your power consumption, like one of the houses in the blocks blows, you might shut down that city block, but the block next to you is going to be okay. For example, most hospitals have their own transformer. So if someone blows the power, all of their machines don't die immediately. It also allows you to control the voltage versus current that's coming into your wherever you have your transformer hooked up into. And let's talk about how that's happened. So I have a source that has a coil of wire around this. And this rectangular thing, it's just a big hunk of metal. Okay. I have my house or whatever. It is hooked up to the other end, where I have a number of turns going in. So how many coils of wire I have. I have a number of turns going out. I also have a voltage going in and a voltage going out. And of course, I have a current going in and a current going out. Okay. Now, what's going to happen here is as this AC source wiggles its current up and down, it will create a magnetic field through these coils. And however often its current wiggles up and down, the magnetic field is going to flip. Since this is a hunk of metal, and we make sure it's a paramagnetic sort of metal, that magnetic field will exist throughout the whole thing. So if I make my magnetic field with my current going in, my coils on the other side will see it. And they'll see that magnetic field flip up and down as well. And then by Faraday's law, what we will have is we'll have a changing magnetic flux through a loop of wire. So on one side, I'm going to have this flux that's being created. So I have a flux over here in. And on the other side, I'll have the same flux going out. And in fact, they're going to have the same rate of change. What might be different, though, is the number of coils on each side. So if you remember, Faraday's law talks about the number of coils times a change in magnetic flux. So basically what we have here is this change of magnetic flux is the same, but the number of coils and therefore the voltage will be different. Sound okay? Okay, so on the inside, d flux in dt, that's going to be the voltage in divided by the number of coils in. On the out side, you have the voltage out over the number of coils out. So I'm hoping that you can see that you can control what your out voltage is by just varying the number of coils. In out over in. So if you have more coils on the outside, you'll get a higher voltage. If you have more coils on the inside, you'll get a lower voltage. Valid? However, energy is still conserved. So what has to remain constant is that the energy in has to equal the energy out. And not only the energy in and out have to be the same, but the rate of change of that energy. Rate of change of energy, that's power. So the power in has to equal the power out, just because of conservation of energy. Power equals current times voltage. So power in has to equal power out. So the current in times the voltage in equals the current out times the voltage out. Let me write that so it all fits in one line. Current in, voltage in, current out, voltage out. Okay, sweet. This is nice. So if, for example, you ramp up your voltage, what you're doing is ramping down your possible current, and vice versa. Generally, if you're going from power like your power station to your home, you want to ramp your voltage down. By the way, that's step up. So if you're ramping your voltage up, that's a step up transformer. You're ramping it down, that's a step down transformer. And now let's look at why you care. Okay. What do we get our power here? Hetch Hetchy? Right? That's where we get our power. Do we not know where we get our power in San Francisco?
I don't live here, so.
Okay. I think half of it's from the Hetch Hetchy Dam, and then like there's a whole lot of windmills like out there. Okay, so we generate the energy out there. We have to get it back to here, right? So you have to run it through wires. No matter what, if you have like, no matter how nice your copper is, at some point the resistance of that wire is going to get pretty high. Does that make sense? Okay, so if you just direct current your power, let me run 25 amps through this wire. Once it hits your city, the amount of energy that you have just burned up is not astronomical. We're here on Earth, but a big number. It's very inefficient, super wasteful, because you're having to transport a whole lot of energy. Your resistance is going really high. It's just not working out. Okay, so if you want to transport electrical energy, you want to do it at a low current and therefore a high voltage. So power is what we can't, you can't fix power. Energy is conserved. We can't change that. But what we can do is we can say, let's dump our current really low, ramp our voltage very high, and then just try to transport this potential difference. And potential difference is nice, right? Because nothing has to move for a potential difference, right? Like I have a capacitor, nothing's moving, it just has a potential difference. So you don't have to worry about that high resistance because you're not running a current through your wire. You're just making a potential difference appear, which means that this power coming into your city is coming in at a very high voltage and very low current. Then you run it through a series of transformers to ramp down the voltage up the current. So at the end of the day, you can actually run like multiple devices in your home at a reasonable voltage. Does that make sense? Okay, and that's why transformers work. And this works even better when you realize that you can play games with this power factor as well. Because if you're out of phase, you got a really nice like no burning off of power. You're just storing the power between your capacitor and your inductor, which is why AC power is a thing that we do and DC power is not a thing that we do. Okay, I think I'm done. Are there any questions? I haven't done like any homework problems How's this chapter working out for you guys? Okay, I would be, so next week we have electromagnetic waves, which is a pretty flexible subject that we can look at. I would be okay doing a couple homework problems from this chapter next week if you wanted me to. Are you guys interested in that?
Yes.
Okay, then why don't, I'm gonna move the homework to be due next week on Friday. The next chapter will be due that day as well. But come to class on Tuesday with any homework problems that you want done. Sound okay? No homework due Friday, but 2 chapters will be due next Friday. We do have a quiz. Okay, online people, are you guys okay?